Hi, my name is John Nair, and now, as a team with my friend Arda, we're going to present our poster regarding set theory. Now, sets can be defined as an unordered group of objects or a collection of objects. The notation E denotes that an object is an element of a set, and this notation denotes that an object is not an element of a set. Now, sets cover an important part in mathematics and therefore are very important. And this poster aims to convey the key information regarding sets. Now, we first come to the representation of sets. There are three parts to this. First way to represent sets is to list all elements in curly braces. This is also known as the Brewster method. For an example of this, we may look at this, the set A of odd integers that are less than 12. As you can see, we've written every single odd integer that is less than 12. The second way to represent is to list some of the elements and use ellipses when the general pattern had become obvious. Now, for an example of this, we may look at this, which asks for integers that are less than 300. As you can see, we've written some of the integers, and then when the pattern became obvious, we put ellipses. And the third and most popular way to represent sets is to use set builder notation. And for an example of this, we may look at the set P of all odd positive integers that are less than 50. As you can see, there are two ways to do this. This notation here means such that, and the entire notation can therefore be read as x, such that x is a positive integer less than 50. And the second one also has the same meaning, the empty set. Now, empty sets are special sets that have no elements in them and can be represented by these two notations. An example of an empty set is the positive integers that are greater than their squares. The singleton set is a special set that has only a single element inside it. And this set is also a singleton set, which has only one element inside it, which is the empty set. Now, for another example of this, we may look at this example, which says that every element of A is a natural number, and the square of all these elements is equal to 4. There's only one element that satisfies these conditions, and it's 2, and there's only one single element, and because of that, A is a singleton set. Subsets. Now, we say that A is a subset of B, which is shown as this, and which can also be expressed as so, if every element of A is contained within B. But if every element of A is also contained in B, but there is also another element or more than one element that are contained in B and not in A, then A becomes the proper subset of B, which is shown like this. A set will always have the empty set and itself as its subsets. Now, if a set has n elements, then it has 2 to the power of n subsets and 2 to the power of n minus 1 proper subsets. The minus 1 represents itself. For an example, the empty set has 0 elements, therefore, from 2 to the power of 0, it has one subset, which is itself. The naive set theory, which was first stated in 1895 by German mathematician Georg Cantor, says that a set is a collection of objects, but the meaning of an object was not specified. And because of this theory is an intuitive definition. However, we will continue to use this set theory, even though it may lead to paradoxes. Now, Venn diagrams. Venn diagrams are used to visually represent sets and are named after John Venn, an English mathematician. The universal set U is which contains all objects under consideration, is depicted as a rectangle, and all subsets of U are depicted as circles and or other closed curves within U. Now we move on to our next topic, which is the size of a set. We use the size of a set in counting problems and therefore are very important in our understanding of sets. Because of that, we will define the size of a set as the number of elements within a set. Also, the cardinality of a set has the same meaning as the size of a set. For an example of this, we may look at the set of negative integers, which is infinite. Now, finally, we come to our final topic, which is the power set. If S is a set, then the power series of that set is all the subsets of that set, meaning that all the subsets of a set make up the power set of that set. For an example of this, we may look at this question, which asks, what is the power set of the set 1, 2, 3, and its cardinality, which is also has the same meaning as size. Now, for the solution of this, we will write every single element or the subset of the power set, of the element of the power set, which is the subset of this original set. Do not forget the empty set and itself. And if we count all of these, it will give us the answer of 8. However, there's another way to find the cardinality of power sets, and it's much more easier than writing every single subset of the original set. And it is by using this formula, which states that if there are n elements of a set, then its power set has 2 to the power of n elements. Therefore, from 2 to the power of 3, we get 8. Thank you.
I'm Arda. Today I'm going to talk about the set operations. We are using set operations to obtain new sets and new numbers. The basic set operations are union, intersection, difference, Cartesian product, and complement. Let's look at the intersection. It specifies a set that contains the elements which are from both A and B sets. Its representation is like that. For example, this is the set A and this is the set B. Both of them has these two elements, so their intersection will be equal to this set. Another thing is union. We are using union to combining two sets. Its representation is like that. This is set A and this is the set B. When we combine them, we obtain a new set, and this set contains all of the elements from the set A and set B. The complement, it points out the elements that a specified set doesn't contain. For example, set A contains these elements, but set A doesn't contain these elements, so it's equal to A's complement. Another thing is difference. Gives the set of elements that only one of the two sets has. Its representation is like that or like that. Set A contains these elements, set B contains these elements. Set A contains them, but set B doesn't contain these elements, so A difference B equals this. Another thing is set identities. We are using set identities and laws in the set operations. They are very useful laws, so we must keep in mind them while we are solving these problems. Another thing is Cartesian product. We are using this to creating n-ordered tuples. They are very useful to ordering sets. Its representation is like that, and this is the example of a Cartesian product. Okay, next is generalized unions and intersections. We are using them to creating formulas and performing same operation to different sets. This is for union and this is for intersection notation. Last one is multisets. Multisets are sets that some of its elements are repetitive. For example, set A contains 4 2 times, so it's a multiset. Okay, let's look at problems. In a class of 100 students, 35 of them likes physics, 45 of them like chemistry, 10 of them likes both, and we want to find how many of them neither of like. X plus 10 equals 35 because there are 35 physics students, and A plus 10 equal 45. The people who likes chemistry is 45, and 10 of them likes both. So X equal to 25, A equal to 35, and their sum is equal to 70. Also, 70 plus D must be equal to 100 because there are 100 students, so D must be 30. That means there are 30 students that likes neither of them. Last problem is Drawing the Venn diagram. Okay, this is A, this is B, and this is C. A intersection B's complement is this area, and union A's intersection with C's complement is this area. So all of the shaded areas are the OR answer because it's union. Okay, in conclusion, the sets are pretty important topic in computer science. So as a computer science student, we must know this topic very well. Thanks for watching our presentation.